this is going to be about the mathematics behind the pairings, actually how they work, why they work. This is what I want to kind of tell you. You have the slides in front of you. It's probably going to be way too many slides and much too technical at this point. So the slides are also kind of intended to be a little scriptum or something. So I might just, well, it's probably bad style, but I might just skip some slides during the talk. And you are left to read them at a later stage if you're interested in at home, I guess. Yeah? So in the beginning we will be fairly thorough, rigorous, I guess, but later on I might skip here and there, and then you can read at home if you want, yeah, or whatever. Okay, let's see. So first some general remarks. So this one is not very well familiar, but let us just recall here. So this is the general pairing setting. We have the three abelian groups. So at the moment it's abelian groups, not cyclic groups, and I want to specialize later on. And then we have this non-degenerate bilinear map from the groups into the target group, right? That's what we always have. And then bilinear here. So here's maybe the first twist that one should, in notation here, since it's all going to be based on elliptic curves, and those two groups will be subgroups of elliptic curves, I write the group law in additive notation. Yeah? And since the target group is going to be in the finite field, the group law is written in multiplicative notation, so here's the multiplication. Yeah? But this is just notation. Yeah? I could just exchange plus by multiplication or vice versa. I mean, doesn't matter. I mean, it's just abelian groups, and it's only a matter of notation here. Okay, so this is the bilinearity. Of course, I can also do this n times, and then you see it's just like putting an exponent n or a scalar multiple n into the exponent here, if I just iterate it n times, for example. Yeah? So then it's also supposed to be non-degenerate, which means the following. So whenever I plug in something here which is not 0, then I can find something here which is such that the whole pairing value is not equal to the neutral element of the target group, which is 1. Yeah, so whenever I plug in something here, I can find something here such that I get something not equal to 1. That's a standard definition. Okay. Yeah. So this would also be for non-prime group here in this case. Yeah? Yeah, sometimes, for example, what you see, so if it's, for example, cyclic groups of non-prime order, you would also see the definition that the value on generators should be a generator. But this would be equivalent here, yeah? Because, for example, if I take two generators and I would get something not equal to 1, but it might not be a generator, but then there's a cofactor missing. I introduce the cofactor into here, then I have a value and something else here, and I would always get 1, yeah? So then it doesn't work. So this is kind of equivalent. Okay. Yeah, so here are examples. Yeah, not interesting for cryptography at the first place. Of course, the scalar product is a bilinear non-degenerate map. Yeah? Euclidean scalar product on real or affine real space, on Euclidean space in n dimensions. That would be an example. Another example, which is kind of more relevant now, is multiplication in a ring or maybe in a field. Well, I should say maybe without zero divisors, whatever. So multiplication in the field is also a bilinear map, yeah? Non-degenerate as well. So why is it non-degenerate? That would be the case. Well, anyway. So no, let's skip this at this point. So and these are the prime examples that will show up in our case here. It's those Weil and Tate pairings on elliptic curves and more general abelian varieties, whatever that is. That are also non-degenerate bilinear maps, and these are the guys which are used in cryptography. Those guys are not used because they would not be secure. Okay. So what do you do with these things? Well, you know it from this case. It's good for linear algebra. Yeah? So if you want to solve the linear systems of equations, for example, then you can kind of use this one here. If you have a system of orthogonal vectors, for example, then you can write if you want to write a vector as a linear combination of these orthogonal vectors, then the scalars which you have to look for are just values of this thing here. And similar stuff actually is then also applicable for in the cryptography case. You can use these thingies to do linear algebra on elliptic curves in some sense. The only problem is that you don't get a nice scalar out, but maybe something that is kind of twisted a little bit. Yeah? But it's kind of similar otherwise. Okay. So, as I said, these two other pairings are not useful for cryptography because they are not secure. So what means secure? Yeah, here like everywhere else in cryptography, we always need the following. We need to have something where we can compute forward in an easy way, and going backward should be hard. Yeah, that's the basic principle. And for the pairings, for example, for the scalar product, we can kind of compute forward, but we can also kind of compute backwards all the time. So that's always easy. Also for this guy here, yeah. So if for example, x times y is equal a, I just multiply by x to the -1 and can solve for y, and then I can basically went back, for example. No? So this is just solving of linear systems. And what we want to have here in the cryptography setting is, that basically solving of linear systems should be hard. That is basically the thing one wants to have. So here is, okay, so let's see. So first of all, efficient computation in the forward direction. So we want to have that the group laws on G1, G2, and GT, they should be efficiently computable, of course, with efficient representation and so on. Yeah, you fill it in what you need. Of course, a quality test should also be efficient, sampling of random elements as well. And then plugging the stuff in, anyways from here and here, plugging into the pairing should also, and then the computation of this value should also be efficient. Yeah? That is stuff one wants to have. So what comes out is, in the cryptography setting, usually these groups are prime order groups, cyclic groups of prime order, but different groups. But of course, mathematically speaking, they're all the same. Yeah? I can make an isomorphism from these groups to each other one. Yeah? So because it's just cyclic of prime order, they're all isomorphic. The only problem is that from the computational aspect, I might not be able to compute these isomorphisms. But otherwise, from the logic, they're just the same. Yeah? Yeah, this is really important. Yeah, this is extremely important. Yeah? So in some applications, so for example, one question. So what is extremely important is you can throw it all to the garbage if you can compute if you can compute from here to in any one of these two. Yeah? That is very bad. From G2 going back to from GT going back to G2 or G1, that should really be difficult. But going from G1 to G2 is easy, yeah, because I just take a fixed argument, and whenever I plug in an H, well, I go from G2 to GT. That is easy. Yeah? So from G2 and G1 going to GT, that's always easy, but the backwards direction should really be hard. Yeah? And going this backwards direction is solving linear algebra problems, basically speaking. Okay, so this is so basically speaking, they're all prime order cyclic groups. They're kind of isomorphic, mathematically speaking, at least. What one also wants to have is usually that there's a nice, unique representation of these elements somehow. But it's not absolutely necessary. Okay, so here's what I was actually pointing at. We also need some high complexity assumptions, going backwards, basically speaking. So this is what relates to your question here. Going back from GT to any one of the codomain groups should be hard. Yeah? Otherwise, it's not good enough. Well, sometimes, not always, we also don't want to be able to go from G2 to G1 or the other direction. And sometimes we actually do want this. This really depends on the protocol which is used. Yeah? Sometimes we really want to go from G2 to G1 and also backwards. This should be efficient. So this is just the case of the so-called symmetric pairings, where the two arguments are basically the same. Yeah? But sometimes you actually don't want this, and then it should not be possible. Yeah, and then there's a host of problems related to this. So here's maybe the next, probably the most basic. This is this bilinear Diffie-Hellman assumption. So suppose we have the two codomain groups are the same in this setting. Then suppose we are giving these 4 elements. Yeah, but this is always a little bit deceptive. Yeah, at first reading, you read this and okay, so you're supposed to compute this guy here. So and you think, okay, so what do I have to do? E of GG, yeah, this is easy because it's just a pairing computation. I'm supposed to be able to do this. Yeah, and then I just take A, B, and C and raise this here to the power. Should not be so difficult because I'm giving this. Well, this is my input. Oops. And I'm supposed to compute this. But the point is, this is kind of in this notation, it's usually a little bit implicit. I'm giving the elements, not the exponents. Yeah? So what is written here are elements of the group, not the exponents. Yeah? So I'm giving some weird bit representation of some objects, and this only suggests that there is an A and a B and a C, such that these 3 elements which I'm giving are equal to G to the A, G to the B, and G to the C, but I'm not giving A, B, and C. Yeah? So in some sense, the task is, you could think, find out what A, B, and C are, and then compute this guy. But finding out what A, B, and C are would be solving a disk log problem. Yeah? But maybe there are tricks with, to compute this guy without finding out A, B, and C. Well, it seems hard to be possible, but there's no proof. So maybe there's various tricks without computing A, B, and C and still computing this guy. Could be the case. So this problem is less strong than the disk log problem in the group G. If I can solve the disk log problem in the group G, then then this problem would be easy. Okay, so this is something you want to have, and here's another thing. Suppose I get rid of this one element, then in fact the whole problem would be easy. Yeah, so maybe I should use this one here. Oops, where's the it's not on the slide, but if I have, well, let's see, I should clean a bit. Okay. So here is G. Yes? Black is better to read? Okay, thank you. That's work. Okay. So now I'm giving only 2 of the guys, and the problem is to compute this. So this would be just with 2 elements, not with 3. And I claim it's easy. Yeah, well, I just plug it in, right? I plug the 2 elements in, I use the bilinearity, and I get with the A and the B. Right? So in some sense, doing a multiplication of 2 elements, it would be easy, but doing 3 should be difficult. Or more. Okay. So there's the zoo of problems and references where they are used can be found, for example, in this document. There's just a list of hard problems in cryptography and where they actually occur. It's kind of interesting to see. Okay. So here are some general musings about pairings and what they actually are in a conceptual way. So at least from the math side, a typical construction is this one. The first year students always hate this. So you take again the vector space of dimension n of the real numbers, and then you look at the dual vector space. So it's the space of functions from here to here, basically speaking coordinate functions, in some sense. And then target group would be this, and then a typical non-degenerate bilinear map is function evaluation. You take one of these dual vector space elements, you take an argument, and it's just evaluation of the function. And this is basically the prime concept to make a non-degenerate bilinear map. And the cool thing is, in this curve-based setting, of the Bar-Ilan pairings, it's in some sense precisely this concept that is used. Okay. But when you now think of, can I also do 3 arguments, or can I also make a trilinear non-degenerate map? Then it's a bit difficult, because what would be the third thing here? So it's not so easy to see. Of course, you can kind of iterate the whole construction, but then it gets very nested and seems not very natural. So this is also maybe one of the problems why this setting has so far not been generalized to pairings other than bilinear pairings. Okay. So here's another view. Okay, so from the mathematics, we at least know the groups are actually kind of the same. The only problem is we can't compute between them because they have different bit representations. But otherwise, we can think we have just a group, and we only have 3 ways of representing the elements in different ways. And we can't convert between those bit representations. Okay, so so now suppose maybe it's not as bad as we thought. We can convert between bit representations a little bit. So I can take those bit representations and make the corresponding element in G1, or maybe take one from G1 and go to G2. So if I can do this and nothing more, well, and have the pairing, then I can make a pairing which sits completely on G1. So what do? Here's the formula. I take 2 arguments, x and y. Y is in G1, I need to map to the second argument, but I can do this with the G. I take the Y, I map the Y to the G2. Now I have 2 arguments for the pairing, so this you see it here. I can apply the pairing. then I get a value in G2, bit representation in G2, and now I use the function f to go back to G1. Yeah. E? No, oh yeah, this should be, what was it actually? Yeah, it should be E, yeah. So we had E so far. No, yeah, sorry, yeah, this is actually wrong. Yeah, here's an E. Thanks for the comment. Please take a note in your slides. Okay, so this is the old pairing, we get a new pairing. Huh? Yeah, and now, when you think a little bit about it, oops, we have a group with say, a group law addition. Now we have this bilinear map, but from the bilinear properties we see, it's actually a multiplication. And what turns out is now that the G1 is a black box field. Yeah? So it's a field where we have an addition, and the pairing gives us, well, it's like a black box field. We have an addition and we have a multiplication, and the field is somehow bit represented. Yeah? Well, and I say it's groups of prime order n, so I know it's the finite field with n elements. So when I can do this stuff, yeah, then I know algorithmically I have a finite field with n elements. Yeah? Well, and then it's not so hard to see that the Diffie-Hellman problem is easy and all other pairing problems are also easy. Yeah? Because we have a field and then you can do whatever you want, basically speaking. Yeah? So this is very bad. This is not supposed to be happening here, these thingies. Yeah? Okay. In particular, the f is very bad. The g is not as bad maybe as it could be, but the f is the worst in this case. So no conversion back from G2 to G1 or G2, from GT. That's a kind of silly notation here. So no conversion back from GT to any one of the argument groups. Okay. Yeah, in some sense. Yeah. Well, but that depends on the point of view. I mean, there's a paper of Verhoeven, here it is, well, yeah, the pronunciation is not right, where he compares the security of those groups. So in this setting, he looks at these two groups are the same, and here is a finite field group. And then the argument is which group is more secure. Yeah? And then he says he takes your idea in kind of arguing, okay, if the pairing is secure, then also the Diffie-Hellman problem here should be secure. Yeah? One can also argue that if this is insecure, one could, for example, claim, I have an elliptic curve group G here, this is very secure, and here I have a finite field group, this is not so secure. Yeah? So but I can make a reduction. Yeah? So it's okay. So suppose I have an instance of the Diffie-Hellman problem here. I can map it to an instance here, and if I can solve it here, I could also solve it here. So it also means that in GT it must be hard. Yeah? So this was this original thing with super singular elliptic curves, where there was a claim, this is they're just kind of different instances of the same group, and there was this argument of relating the difficulty of the two problems. Yeah? But you can put it vice versa. You can say if one is secure, then the other one must be also secure, or if you say, the other one is insecure, then my first one must be insecure. That's the way of looking at it. Yeah? Positive thinking or negative thinking. Yeah, okay. Yeah, so, okay, so what is the moral? Pairings are basically multiplications in fields. We have a field of prime order, we have an addition in the field, and we have, and we have a multiplication. This is given by the pairing. And the only thing is that we have weird bit representations of the finite field elements. Yeah? So here we have one for the first argument, one for the second argument, and the third one for the output of the pairing. So we have 3 bit representations of the finite field, and can compute a multiplication in these bit representations, but we can't map bit representations to the other cases back. That's basically a way of looking at it. Okay. Yeah, and because this is so, we can't also iterate the construction. If I have a multiplication in a field, of course I can also multiply 3 elements or 4 elements. Yeah? But because the output of the pairing is a bit representation that I can't feed back into the pairing, it doesn't work. And that's also one of the security assumptions that we had here. Yeah? For example, with 2 elements it should work, but not with 3. And this basically, it's just this, that we only can do 1 multiplication and not 3 multiplications. Well, we can do only 1 multiplication, not 2 multiplications. Okay, so maybe there's 2 philosophical lessons from this. Multilinear maps would then essentially be multiplication of n arguments in a kind of a black box field or so. And also, if I have a multiplication in a field, then I can also do higher dimensional linear algebra, of course. Yeah. So if I have a field, I can make matrices and vectors and this kind of stuff, of course. Yeah? And this is this idea of the product pairings, basically speaking. Yeah. So if I have this one pairing, and I think of it as a multiplication in a field, only with funny bit representations, well, I just make a product pairing. Yeah? So it's how do you go from how do you make the standard scalar product? You multiply two coordinates and sum it all up. Yeah? So here I multiply two coordinates and would sum it all up. Yeah? I can also have a gram matrix, for example. So if I don't have the standard scalar product, but another bilinear form, then there's this kind of gram matrix representing the bilinear form. I can also introduce those matrices. Yeah? And this is basically what's behind the product pairings here. Yeah? So here it's a bit irritating that it's a product, but we are in the multiplicative setting. Yeah? I could also go to an additive setting. It's just notation, and then you would see it's just a sum, and here's just a linear combination. Yeah? So this formula here is just the usual thing from linear algebra, where you take two vectors and you multiply the one vector like so, and the other one transposed to an inner matrix. This is this formula, and that's a product pairing. Yeah? Well, at least that's the way I see it. Okay, good. So now go to the curves. So curve-based pairings, well, yeah, so those guys would be defined in terms of algebraic curves and their Picard groups and Jacobian varieties. So these are kind of mathematical objects that we don't have to think so much about. Usually, well, you know, they're always bilinear, and usually the groups are taken to be cyclic, and the elements then have nice bit representations. They're unique, for example, and there's various special properties that we are going to talk about. And well, the whole thing embeds also in some more general aspects that it's also not so important, but it's, well, just then you see it's something that is called arithmetic duality. Anyway, so it's kind of general background behind the whole thing. And pairings are also not only used in cryptography, that's also used, for example, in other areas of computational mathematics, for example, when you want to solve certain integer equations. Okay. So now in the following, so we don't do this general stuff. We stick to the case of elliptic curves and keep it simple. Okay. So what I want to do now is just explain a little bit how the basics work, and so you see how it all comes together. So finite fields recap. FQ is a finite field with Q elements, so Q must be a power of a prime. So if it's a prime, what is it? It's z modulo pz, so you take the integers and compute modulo p. Yeah? Well, funny, a common first year's mistake is to some extent, if I then want to have the finite field with Q elements, let's just take z modulo p to the rz. Yeah? But this is wrong, because this is not a field. Yeah? For example, if I take the element p inside here, it's not 0, but if I take p to the r minus 1, it will be 0. So this is a ring with 0 divisors, and so hence it's not a field. So in order to construct a field, one has to do something different, but still similar. One goes to the polynomial ring in X over the finite field Fp, and then one takes an irreducible polynomial and does modulo on that irreducible polynomial. Yeah? And then one gets a field. So then there needs to be an irreducible polynomial of degree r, and then you get this field. And the cool thing is, it doesn't matter which to take. You can take any irreducible polynomial of degree r will give you the same finite field in a sense. Just different representations again. Okay, so here's some properties. They're all contained in each other somehow, as long as the Q2 here is a power of the Q1. Then they're contained in each other. Then there's kind of a biggest finite field, but it's not finite anymore. You can somehow, so that's this algebraic closure. It's basically all finite field stuff into one thing, yeah, in a sense. And but this has the nice property that if I take a polynomial defined over this very big field, it always factors into linear factors. It's like with C. Yeah? So if I, for example, take x squared minus 2, I can't find a solution in the rationals, because square root of 2 is not a rational number. But if I go over R or over C even, then I can always find roots. And this is the same here in that sense. Huh? Okay. Then occasionally this guy here will show up. Let's see. maybe we skip this at the moment. We can go back later because we don't need it for the next half hour. Okay. Okay, elliptic curve, you have seen this, so I can be a bit quicker. So this, so if we look at p, the prime number p should be 5 or bigger. So we don't do 2 or 3 at the moment. Well, the only reason is that for those p, the curve equation is kind of nice, and if I take other p's, the curve equation is a bit more complicated. But otherwise, it's all the same, more or less. So we have these guys here, and these elements a, b are from the finite field, and that's it. Yeah? I mean, there's a little bit, there's some condition that Nigel showed you. Well, the condition means, so the condition looks technical. It's the thing with the -4 a cubed should not be 0. What it means is that this polynomial should have 3 distinct roots. Yeah? This polynomial should have distinct roots, should not have a double root or something. That is what we want to have. Yeah? Okay. Yeah, then there's the set of, so K is now a field containing FQ. Then there's the set of K rational points. This is just all tuples, x, y, where the coordinates satisfy the elliptic curve equation. And then one adjoins, in a kind of a technical manner, a formal element at infinity, which is called O. It's kind of a symbol for the matter of the talk. Yeah? And this can be done for any extension field K of the finite field. So we get different point sets. And the thing with elliptic curves is that these point sets are actually abelian groups, and there's a formula for addition which is given by a rational function in the coordinates. Yeah? So of course any set can somehow be made into a group, I guess. But in this case, the formula is really given by formula. The group law is really given by formula in the coordinates. That's the cool thing. Yeah? And this funny element here will then be the neutral element. And then there's also Hasse-Weil that one knows how, about, but at least but up to a certain error term, one knows how many elements are in the group. If this is the finite field, then we have, well, with q to the r elements, then the number is, well, we have so many points in here, like we have x coordinates, but minus t. And t is kind of an error term, which can only be estimated from above by the square root of the whole thing. So we know elliptic curve has always as many points as the finite field, roughly speaking. But there's a variance possible, and this is the square root of the number of points. Okay. So this what? Say again? This variance. Yeah. Where does this come from? Yeah, how can I mean, this, it's so difficult to answer where something comes from. Yeah. So let's see. I mean, okay, a silly question would, for example, be, there are examples which attain this bound. Yeah? So you can, for example, make examples where the bound is sharp. And that's basically the reason, in some sense, because there are examples where the bound is attained. For example, if there were no examples who attain this bound, then one could probably prove that the bound is lower. Yeah? That's basically the reason. Yeah? You could, for example, ask, why is it the square root? Yeah, this is a bit complicated to explain. I mean, this is no, I don't want to touch it, I guess. This is something to do with yeah. So what I can prove is, basically speaking, you can choose any t here and make an elliptic curve. There's a procedure of making elliptic curves given any such t in a sense. Yeah? And one can just make them somehow. Yeah? And the more interesting part is, for example, why there's a square root here, and there's a heuristic explanation if you want to know this. Which is actually very easy. So suppose I take a random x value here. What is the probability that the number here on the right-hand side is a square or not a square in the finite field? And as it turns out, about half of the elements are squares, and the other half are non-squares. So if I just take a random x here, I have probability 1/2 that this is a square or not. Well, and then for about half the x values, I get a y coordinate, but then I get 2 y coordinates, plus y and minus y, usually. Yeah? So for half of the x values, I get 2 y's, and then I'm back again at the number of the finite field elements. And the cool thing is that the error which occurs in the whole thing is just this square root thing here. Okay, So, but back to the pairings. Yeah. Okay, the addition law here on the elliptic curves is given by formulae, and these formulae are very small. Yeah, it's like up to degree 3 of x's and y's. Yeah, so it's a very small, compact formula to add 2 points. Yeah, I take 2 points, I plug the coordinates into the formula, out come the points for the sum. It's very easy. For the pairings, it's similar. For the pairings, we also take 2 points in some sense. We plug it into a formula, and out comes now an element in K. That is how the pairings work, also with a formula. But there's a twist. The problem is these formulae are exponentially sized, yeah, in the input data. So it's in some sense not possible to write down the formula, unfortunately. Yeah. So here these formulae can be written down, but the formula for the rational function for the functions which define the pairings can't be written down because they're much too big. So they would have a degree, for example, like 2 to the 160 if you write it down. And this is the whole problem, basically speaking. Yeah, why we have to go at what we have to do now. And we can't really write down these formulae in an efficient way, so we have to come up with other tricks to deal with them. Okay. And this is basically this is actually also a general theme in the whole business here. Yeah? You have all these algebraic formula, and then you kind of plug formula A into formula B, and you iterate the whole thing, and they get bigger and bigger and bigger, and it just is a mess. It's a complete mess. Yeah? So, in some sense, you don't want to look at formula. This is a maxim in this area of research somehow. Don't look at formula. Yeah? Try to make it without formula somehow. And this is what gives the whole thing kind of a certain level of abstraction, because now one has to find reasonings which do not look at the formula, but which prove results about the formula somehow. And this makes it sometimes a bit complicated looking or abstract looking. Yeah? But this is also precisely what we have to do here now, because we can't just write down the formula, so we have to have other means of working with these formulas somehow. Okay, so yeah, so what I call a formula here is a rational function. Yeah? It's just an expression. So what do these expressions look like? So I take an f here. Oh, okay. So what is written here? So there's this guy here. It's a field of k rational functions. And what is it? This is the following. Yeah. We just take a numerator. This is a polynomial in x and y. This guy here. And this guy is also a polynomial in x and y. Yeah. So easy. Yeah. Just a polynomial x and y. Polynomial x and y. The coefficients are from the k. So this is indicated by the k here. This is a representation of an element of this field. Yeah, and why is it called a function? Yeah, this is called a function for the following reason. Yeah, I can take a point. So now this is the algebraic closure of k, so it's kind of a field bigger than k, say. I can just take a point here, and I can do this guy. So what is this? I can map the point to f of p, so I evaluate the function at p. And how is this done? Well, the point has an x and a y coordinate, and I just plug the x and the y coordinate inside the x and y, which is given here. Yeah, so it's very easy. Yeah. So taking coordinates, plug it into here and here, compute the value, and out comes something in k. That is a rational function, basically speaking. Well, there's only one problem. Ooh, what happens if I get, for example, a value non-zero here, and here will be 0? This can happen. Yeah, then I'm kind of screwed a little bit at least, because then there's no sensible value in k, and for that reason one extends the whole thing here by a symbol infinity and says, okay, then it takes the value infinity. Yeah. So usually it's easy to compute, just plug in, and if something comes out here and something comes out here, you can compute the value. If, for example, 0 divided by 3, then the value would be 0, of course. And if it's 3 divided by 7, then it's 3 divided by 7. And if it's 3 divided by 0, then it's infinity. Oh, and what do we do if we get 0 divided by 0? Then you have to recap what you did in analysis, I guess, in first year calculus. There's this thing of L'Hopital, this rule, where you do it with the derivatives. And then you can resolve this case, and you can do something similar here. But there's also good news. We don't have to do it in the talk, because it does not occur that we have 0 divided by 0 or infinity divided by infinity. That would be the other case. We can avoid this in pairings, so we don't have to deal with it. Okay, so here are some examples. Finite field with 5 elements, elliptic curve. Well, here's the points. Well, that takes a little bit of computation to find that these are all points. How many is it actually? 1, 2, 3, 4, 5, 6. So it's about like 5 points in here. Yeah? About correct. So we take these 2 points here. Now we take, here, these are very, very nice functions on the curve. I take the x-coordinate function, just the x. And if I evaluate this function at the p, well, I have to plug in the 2 from here into the x, and I get, of course, 2. And what happens if I do it with the q? I have to take the x-coordinate of the q. I get -1. If I do it for the y, I have to take the 0. And if I do it with the q here for the y, I have to take the 1. So just plugging in the values. So what happens if I take this function? Well, let's see. For the q, I should divide the x-coordinate of q by the y-coordinate of q. So -1 divided by 1 is this. Okay, -1 comes out. What about p? X-coordinate is 2, y-coordinate is 0. Oh, I get infinity. Okay. Let's look at this function. If I plug in coordinates here, I always get 0, because this was just the definition of the point coordinates. So this function is always 0. And this shows something. The functions are not uniquely represented by their polynomial expression. This function is the same like the 0 function. So this has always this is something one has to keep in mind, that one can change a function by stuff like this in order and get the same function out. For example, here, it doesn't really occur in the rest of the talk, but just to see how one can apply this. Let's look at this function and plug in p. So if I'm plugging in p, I get so the y-coordinate of p is 0. Well, yeah, here is 0. I get 0. If I plug x into here. So what is it? 2 to the 3 is 4 is 8. Yeah, modulo 5 is 3, and 3 plus 2 is again 0. Yeah? So I get 0. So here I have the case 0 divided by 0. How can I repair? Well, I can take this function. Then I can, for example, extend numerator and denominator by the y, like so. Then I have a y squared here, but the y squared is the same like this on the curve. So I can actually I can replace the y squared by this guy, but then it cancels with the numerator. And out comes y. And for y, I get f of p is equal to 0. So then I have my function value. So this would be, for example, one way of resolving these cases. Okay. So let's see. So also back from school, you know, I mean, you can also do this with rational functions in just one variable, and then you have the affine line, yeah, and you plug in values, and then usually, these problems are, what is the 0, the multiplicity of the 0 of x squared minus 3 at I don't know what or so on. So you have zeros, also sometimes poles, and then you say, what is the order of these guys? And in this case, you can do the very same in this more general setting here, yeah. So okay, so if f of p is 0, then we say, point P is a 0 of f. And if infinity comes out, it's a pole. And the cool thing is, one can also attach precisely defined orders to zeros and poles. And usually the pole orders are then kind of taken negative. Yeah? So a 0 of order 3 minus, a 0 of order 3 would be one example. And a 0 of order minus 3 would be a pole of order 3. Okay, so then there's, so what is this? So there's two things, how can one picture this, the whole situation. One is the geometrical interpretation of these numbers. Well, yeah, I just look at the intersection multiplicity of the curve defined by f equals 0 and e. So what is this supposed to mean? Okay, so if I take a parabola and I take the x-axis, then one says, the 0 has a higher order because the parabola is kind of smoothly contacting the x-axis. Yeah? If I just had a line crossing if I just had a transversal intersection somehow, I would say, it's a 0 of order 1. But if it's kind of approaching smoothly, then it's a 0 of order 2 or higher, depending on how smooth it approaches. And the same thing can be done for the elliptic curves. Yeah? If you remember the picture of Nigel, maybe I should write it on the blackboard again. So let's see. So here I can have a curve, and of course I can make, for example, like a tangent here, and then I can look, how smoothly is the curve approaching the tangent here. Or I just do, for example, this is the easy case. Here we have transversal intersection, then the multiplicity would be 1. But in this case, one has to look a little closer what the multiplicity would be. Okay. So this is one picture. The other way of thinking is, if you know a little bit of complex analysis or so, then what's done there is usually that you write functions as Laurent series expansions. So, well, you have power series, yeah, but Laurent series are ones which start with a negative exponent of the variable inside it. Yeah. So let's see how these things look like. So I could have, for example, x to the minus 1 plus x to the 1 plus 7 and so on. So they start at some value here, which can also be negative, and this value where it starts, that would be the order. So in this case, like here, I would have order minus 2, so it would be a pole of order 2. Yeah? So if x if x goes to 0, I have a pole of order 2 here, and if it's positive, I would have a 0. Okay, that's basically it. Yeah, and then one can do some formal properties of the whole business. Well, f of p is 0 or not 0 or infinity precisely when this order is bigger than 0 here, then we have a 0. If the order is 0, then the function value is not 0 because it's neither a 0 nor a pole. And if it's negative, I have function value infinity. And then there's rules. If I, for example, take the product 2, then here should be addition. So here I sum the values. Yeah, please correct. So this, you can see it from here. If I take two such expressions, and if I multiply them, for example, x to the power of minus 3, if I multiply the two guys, I get x to the minus 5. So if I write it here, x to the minus 5 plus I don't know what. If I multiply the two guys, oh not my 5 minus 3 was what I wanted to have, then I get x to the minus 5 plus higher order terms. So this is basically this, and all the other rules that we have here are the same. So if I sum the two things, then it's greater or equal to the minimum of the two orders, and if the two orders are different, then it's actually equal to this minimum, and so on. Yeah. And order is infinity. 0 of infinite order is can only happen if the function is identical 0. Oopala. So these conditions are all very easy to picture when you have this in mind, with these Laurent series. Okay. So here's an example. We take a line. This is the equation of a line. Should not be constant. Yeah, that's this condition here. So from algebra you should know that f intersects E in 3 points, and they can be labeled like so: p, q, and minus p plus q. And if the p is 0, then we have a fixed x coordinate. It means we have the vertical line. That is this one. And when does this happen? So in terms of points, it happens precisely when q is minus p. Yeah? So if I have p and minus p, the points are kind of vertical on top of each other. Okay. Yeah. So if this line does not intersect E, then the order is odd p of f is 0. Otherwise, if there's intersection, we have order greater or equal to 1. So if it intersects E but is not tangent, like in this case, then the order is 1. But if it's tangent, the order will be higher. So and if it's tangent, then there's only two cases left. Depending on p, if p is not equal to 2 minus p, to minus 2p, then the order is 2. And else, the order would be 3. That's the way it comes out for linear functions. Okay. So what about the infinite point? Now, in this case, the geometric interpretation is a little bit more complicated now than the analytic, because it's not quite clear where this infinite point is when we just draw an affine picture. So it's sometimes more useful, I find, to go to the analytic interpretation now and look here. Yeah? So what does it mean? So if x and y tend to infinity, who is tending faster to infinity and who is slower tending to infinity? Well, yeah, if x tends to infinity, well, because of this equation, we know that y squared and x cubed have the same speed of tending to infinity, because otherwise the equation could not hold. Yeah? So, but this means that y has kind of speed 3 and x has speed 2. And this is really true. Yeah? So the order at infinity, so for p equal, of y is minus 3 and the one of x is minus 2. So and then if you look here, well, yeah, if this has order minus 3 and this has order minus 2, then the whole f has order minus 3 if this term occurs, and if it doesn't occur, we have only minus 2. We can also apply this, for example, to this guy here. Okay, this has order -2. This guy has order -3. Now I have to subtract the orders to get the complete order of the whole guy. So -2 minus -3, I get 1. So this guy here has order 1 at infinity. Because it has order 1, I know f of infinity is 0. Which now would be hard to tell because we don't really have coordinates to plug in. And if I take 1 over f, I would have infinity. Okay, high degree rational functions are more complicated, and fortunately we don't have to use them. Okay, so here's another thing. So this is just somehow a divisor for convenient notation. So what is a divisor? Yeah, you can, if you want to use a computer science notation, you can think of an associative array, yeah, data type, where the points are the keys and the values are integers. Yeah? This is basically what it is. But then you also define a formal sum, and this, this is the way you interpret them in addition. Yeah? So what you do is you write it like so. So this is the notation for the whole thing, but the logic is like so. We take this is all points of this elliptic curve here. And then we take this would be the key. It's a point. Well, just a square bracket just to tell that it's a key. And these are the values. Yeah? And then the idea is that one can add the two guys by so if I add two divisors, I look for the same key. I just add the integer values. This is how to do it. Huh? So this is basically it. Huh? And then one also wants to have that only for finitely many keys, the integer values are actually non-zero. This should be a finite sum. Yeah. Okay, so this is the sum of divisors taken coefficient-wise, identifying same keys, basically speaking. And one can also make a degree. One just sums up the value is lambda p here, and this would be the degree. Yeah, so here the lambda p's are defined as this guy, so I don't have to use it later. And just summing up all these orders here, all these lambda p's would give me the degree. It's just an integer, can be negative, right? This could also be a negative integer. Like here, yes? Here, I mean, in some sense, the degree of this guy is -2. Okay, so the whole thing, so the degree function is additive, and here's another definition that we're going to use is we say D is supported in this point group if all the points occurring in the D are actually from E over K. So this is usually a very big field, and we want to avoid working with it, and so we just restrict to divisors where the points are only from the small field here. Okay. Yeah. So if you have a function, we can make a divisor out of it. So we just look at all points and take the orders of the function at the points. Most of the time it will be 0 because the function is defined, doesn't have a pole or 0. But at the points where the function has a pole or 0, we have positive or negative values here. But since there are only finitely many poles and zeros, the whole thing will be a properly defined divisor. So, and divisors of this form, which come from a function, these divisors are called principal. Divisors which come from a function are called principal. You might, for example, start with a divisor and you ask yourself, is it a principal divisor or not? So then the question would be, can I find a function such that the divisor is equal to this? So as it turns out, the degree of principal divisors is always 0, as many poles as zeros. And is, for example, easily seen with polynomials. Yeah? So for example, if I take x squared, this has a 0 of order 2 for x equals 2. For other x's, it does not have a 0. But if x goes to infinity, it has a pole of order 2. And then I have 2 minus 2 is equal to 0. This is kind of a higher general here. Okay, and this is one important trick here. If I have a divisor of a function, then the function is almost completely determined by the divisor. The only thing which is not yet fixed is which constant multiple to take. So if I multiply a function with a constant, poles and 0 orders do not change and the divisor stays the same. But otherwise, the function is uniquely determined by its principal divisor.
Can you redo the example? The x squared example?
X squared?
Maybe you write it down.
Yeah. I should do this one here. I mean, the x squared example is not for elliptic curves, so it's for lines in some sense, but it shows you the principle. Yeah? So if I have x squared, so what is the 0? It's only for x equals 0, right? And then we have order, where x is equal to 0 of x squared is 2. Okay, there's no other zeros. So now let's look at infinity. Poles. Yeah, where x is infinity, because then x squared goes also to infinity. Yeah? And then we see from the exponent it has kind of speed too, which means this. And then we have, what is the divisor? Do I actually have a, let's see. So the divisor would be 2 times x equals 0 plus minus 2 times the point at infinity. That would be the divisor. And summing up the values here, you see 0 comes out. So why do we do this? Why do we do this? Keep in mind, we have to deal with rational functions, and we have to deal with huge rational functions. And one way, and the idea is, maybe we can do it via divisors, yeah? Because, instead of working with a function f, I could, up to a constant, work with a divisor, because it's described by the divisor. Yeah? And why would this be any useful? I show you another example here. Kind of, it's really at the heart of the matter. So this is, let's take this guy, and let's, just with 1,000, that's enough at the moment. Oh, no, let's do it a bit bigger. Yeah, okay. 10 to the 100, okay? So, of course, if I was silly, if I didn't know this, I would have a hard time computing, because then, oh my goodness, yeah? So then I would have to, well, I can actually write it down, what I have something, yeah? X to the 10, 100, minus 1, and so on. So I have 10 to the 100 terms here that can't be stored somehow. Huh? But, well, I started out the example like so. Somehow, this big thing has an inner structure. Namely, I can write it as a linear factor to some high power. This is something special. Not all polynomials of this form would be writable in this way. Yeah? Most of them not. But this is. Well, and now you can decide for yourself which representation is better be stored in a computer. This one with the 10 to the 100 coefficients, or this one with one coefficient and an integer number. Yeah, so this one here has 100 bits. Well, it's a big number, but only has 100 bits, yeah? So to speak. Or maybe 300 bits. Yeah? So 300 bits here, and one number from a finite field, superbly efficiently stored. Well, the divisor of the guy, what is the divisor of the guy? Well, the divisor here would be, well, we did this example here, 10 to the 100, x minus x equals to a, minus, so the guy at infinity, right? So if you don't care for constant multiples, I could kind of store the function using this data representation up to multiples, which is compact. And this would be very bad. Yeah? Okay, but this all worked out because, well, I made the example so. Huh? Okay. Yeah, so here's the same business. Well, this is the example for just if I just have one variable. Here's the example for the lines at the moment. I guess it might be a bit technical to look at the whole thing at the moment. So what the formula? So let's not go into the details. This is something you can look at home. Then, if you are interested in the upshot of the whole thing is, if I have a line, I know that the divisor is of this form. And the line itself was, as we have seen before, was described by the 3 points with which it intersects the curve, possibly with multiplicity. Yeah? So every line intersects an elliptic curve in 3 points with multiplicity. So it might also be only 2 points, but then 1 point with multiplicity 2. That's the meaning. Or maybe it intersects the curve only in 1 point, but then with multiplicity 3. These are basically these cases here. Yeah? But whatever case is, so I'm actually not minding whether P, Q, or these guys are somehow equal or not. in any case, we know that the divisor would be of this form. Yeah? And if P and Q are equal, then I would have 2P. And if this guy is also equal to P, well, then I have 3P minus 3 infinity. Yeah? So that's all inside here. So this is the same business like here, only for lines and elliptic curves. Okay. So, as we have seen, functions can be described by their divisors. There's only this problem with a constant multiple. We had it here, yeah? So where's the pen? What could I possibly do to make the representation unique? What information do I have to add to make to this representation to make the function uniquely determined? Well, if I have this up to constant multiples. So if I now make the additional requirement that it, for example, should be monic in x, so the leading coefficient should be 1 for the highest power here. If I add this to the representation somehow as a condition, then this big function here is uniquely represented by its divisor and this additional condition. Yeah? Okay, and this is basically what's going on here on this slide. So it's also in this elliptic curve setting, it's possible to define a leading coefficient, and it's conveniently done with this point at infinity in some sense. Well, the leading coefficient of f is supposed to be this value here. So what is this? Here's the function divided by this function t to this order. We have seen before that the order at infinity of this guy is 1. So it's easy to see. It's easy to see that the order of this guy at infinity is 0. Yeah, this has order f. This has also order f. So we have order f minus order f makes 0. Yeah? So this guy can be evaluated at infinity. It gives a number, and we require that it should be 1. And this is the generalization to say that that the x should be monic. Yeah. Okay, and here this is also the reason why it's in a framed box. A monic rational function is uniquely determined by its divisor. First step towards the efficient representation of exponentially sized monic f by polynomial sized divisor. Yeah? Yes, okay, let's see. Yes, it's 1:15 now, isn't it? Okay, let's see. This might be a good place. Next slide. Yeah, okay, it's a good place to stop. Okay, so enjoy your lunch.